once you get the hang of binomial probability problems, then the skill is all about just figuring out the wording of the problem and what they're asking for. For example, in this scenario here, they were asking for exactly 4, which means and that's what the formula itself is meant to do. It's meant to find exactly that number of successes. But there are other terms that could pop up. For example, in the one we're about to do, less than. It could be more than. It could be at least. It could be at most. All of those are possibilities, so your job will be to interpret the correct probability or probabilities you need to find. For this problem, they asked for the probability that less than 2 victims knew their perpetrator. You can no longer just let x be 2 and use the formula. It just doesn't make any sense. That's not what they're asking for. They're asking for less than 2. So we're trying to find the values of x in our formula that will give us less than 2 victims. Okay, so since I kind of bricked myself into the corner over here, I'm going to put my aside right under the problem, and then we'll solve it afterwards. So one of the things that's very helpful for students to see when it comes to problems that are less than, more than, at most, at least, whatever it is to see what the probability distribution of your discrete random variable will actually look like. So just remember that from our previous video, that when we were doing probability distributions, we were dealing with the variable x, which listed out all the numbers 0, 1, 2, 3, up to whatever n was, and then the probability associated with them. We're not dealing with the probability now. I'm more interested in the x values for this. So what if I was to create what looks like a probability distribution for this, but I'm just going to ignore the probabilities for now? Then x would be the possible number of perpetrators who knew the victim, or vice versa. So in our scenario, we had 4 was a possibility. So what are all the possibilities? Well, none could, 1 could, and then we could do that all the way up to how many people were queried, basically, or asked. Well, there was a total of 5 victims. So our probability distribution would basically look like this. There would be probabilities down here, and by the way, for what it's worth, we found one of them. This is actually right here, 0.0035, but we don't know any of the other ones yet. We could do the probability distribution for this by using the binomial formula for each one of these, but that's a lot of work we don't need to do. We do know one of them. We're looking for less than 2. So I often say to students, just draw what the distribution would look like and then show what less than 2 would be. Less than 2 does not include 2. It would be these 2. So that means I need to find this and just add them together. So how do I do that? Believe it or not, it's as easy as just using the formula twice. That's it. So we need to find the probability that 0 people knew their perpetrator, and we need to find the probability that 1 did. And when we're done with each one of these, we simply just have to add them together. Very straightforward. So use of the formula twice, so to speak. Okay, so quickly, we would have 5c0, 0.17 to the 0, 1 minus 0.17 to the 5 minus 0. Here we would have 5c1, 0.17 to the 1, 1 minus 0.17 to the 5 minus 1. Just for really quick calculations here, since that part should be the easier part for you, you would get these as your probabilities. And by the way, basically this you could put right there. Technically, if you were building the distribution, this could go right here, and we would have, let's say, 3 of these so far, right? But that's what you would be doing, and that's what a binomial formula finds. It actually finds those probabilities for you. We're not done, though. The actual problem itself, right here, what is it looking for? It's looking for the the probability of 0 plus the probability of 1, which would be less than 2 victims. So we're going to add these two together and get 0.7973 as our probability. Let's move to another example to get some more experience with different types of binomial problems. Suppose that 65% of people pass the state driver's exam on the first try. If 8 adults are selected at random, let the random variable x be the number of them that pass the exam. We can quickly identify this as a binomial experiment by running through our requirements. For this, success would be passing the exam, so failure would not. Each driver taking the test is independent of the other driver, so that's clear. We need a fixed n number of trials, so we know that our 8 here is going to be n for the amount of adults who are selected at random. We also need a consistent p probability, which is going to be 0.65, so this is going to be our probability. So what are they asking? It says find the probability that at least one person passes the exam. The terminology at least one implies one or more. Similar to what I did in the previous problem where I created this nice chart here in order to show what the discrete probability distribution would look like, I did the same over on the right of this problem over here. If we have this time 8 adults selected at random, then the number of adults that could pass the exam would be anywhere from none of them to all 8 of them. So that would generate a probability distribution that would span these values right here. If we're particularly looking for the probability that at least one of them passed the exam, that implies one or more. So our goal in this is literally to find the sum of all of these probabilities. So remember, in the previous problem, we had less than 2, right? And that implied we needed these 2. That means we needed to add these probabilities. So it took 2 formulas to do that. This over here, this would imply that we have to do this 8 times. Give you a hint. Very unlikely that anyone's going to ask you to do this 8 times. That seems a little bit like busy work to me. So there's got to be a better way to do this. Now, you guys do have a background in this. Previous chapter, we talked about probability, and there were at least one problems there. This will basically go through the same strategy. Why? Well, in a discrete probability distribution, we know that the sum of all the probabilities must be 1, or it wouldn't be a distribution at all. So therefore, sum equals 1. Therefore, if we are trying to find this guy here, these probabilities, all of them, the sum of them, you'll notice that there's only one that it doesn't include, and this is the probability of 0. If we can find that value, we should be able to subtract that from 1 and get our orange grouping of 8 probabilities without having to go through and find each one of them. It's actually a very clever workaround that helps us find these types of probabilities quickly. So just as a reminder, we're dealing with, for probability of at least 1, that is going to be equal to 1 minus the probability of 0. This allows us to then use the binomial probability formula to find this right here using the value 0 as x. So real quick, we know that for this guy, x is 0, n is 8, and p is 0.65. So we should be able to enter that into the formula quickly. We therefore have 8c0 for our ncx. We have our probability of success. We're going to be p to the x, so 0.65 to the 0, and then 1 minus 0.65 to the n minus x, or 8 minus 0. We do a little bit of simplifying. we have this. So 8 choose 0 will be 1. And by the way, anything choose 0 is always 1. Anything to the 0 power is also always 1. So then we're just going to have 0.35 to the 8th over here. Make sure you do everything that's in here first and then subtract from 1. If you do so, you will get approximately 0.9998. So therefore, the group of these 8 probabilities, their sum is 0.998, which, by the way, means that this probability here was 0.002. Therefore, there is a 0.998 probability that at least one person will pass the state driver's exam in this problem. Last one of these specific examples, it says find the probability of at most 6 people pass the exam. Okay, in the previous problem, it was at least one person. Now we're at most 6 people. A little bit different. On the right side over here, I have included another probability distribution showing the possibility of successes. If asking 8 adults, that would be 0 all the way to 8. So if I want to know at most 6, that means 6 or less. So that would include all of these scenarios of successes, which means I want to find the sum of these probabilities. This would require, technically, using 7 individual formulas if I wanted to do that and add them all together. There's a better way, just like last time, and that's what we have to figure out. We're going to go along the same strategy for this problem as the last. We know that the sum of all of these probabilities is 1, or it wouldn't be a probability distribution. Therefore, instead of trying to find the probability of each one of these 7 different scenarios of successes, we're only going to find 2. Why? Because if I can take the sum of these 2 right here and subtract from 1, that is going to give me the probability of at most 6. So that's going to be our strategy that we're going to follow. Let's write that out. So the probability of at most 6 going to be equal to 1 minus the sum of the probability of 7 and 8. Now note, this isn't a universal formula. This is just a formula for our problem. That's it. So don't try to bring this and do something, go to a different problem and use this formula. This is pretty much universal the way this is written up here, but this is just an application for this problem. So what do we need to find? We need to find the probability of 7 and 8. So let me pause to write that all out. Here they are. So we have these 2 probabilities have now been computed and can be now entered into the above scenario of at most 6. Make sure you have grouping symbols and such. This is 0.1373. We need to add 0.0319. These 2 together right here make 0.1692. So then when we subtract that from 1, we get about 0.8308. The last thing we need to cover in this section is for binomial distributions, it is very valuable to know their mean and standard deviation. Each one is a unique formula. We have mu for our variable x is always going to be equal to n times p. And we have the standard deviation, our sigma, with our variable x is always going to be equal to the square root of n times p times 1 minus p. For example, returning to our state driver's exam scenario here, where we had the following information. We had n equals, let's write this out, driver's test. So we had n equals 8 people selected at random, and the probability of passing the driver's test was 0.65. So if we want to find the mean and standard deviation of that distribution, we just follow the formulas above. So therefore, the mean of that variable x is going to be equal to n times p, which is simply just, believe it or not, 8 times 0.65. 8 times 0.65 is going to give us 5.2. So what does that mean? That means in this scenario in which there are 8 folks taking the exam, and the probability is 0.65, on average, 5.2 people taking the exam pass it. Next, we see the standard deviation, which is n times p times 1 minus p with a square root over the top of it. That is going to give us 8 times 0.65 times 1 minus 0.65 in that square root. If we do the calculation, we're going to have about 0 or 1.35 as our result.